Greetings, this is the review for the first midterm. It'll be in week number 4. Our format this year is that closed notes and closed book. We will supply scratch paper and the equation sheet. The equation sheet is everything that follows below in what we'll talk about today. Bring a calculator, no smartphones or tablets. Shouldn't be any wireless communications in the calculator. Don't know if that exists or not, and you can't store documents. Bring a pen and pencil, or pen or pencil, and the tests themselves are 8 to 8:30 Monday and Wednesday and Friday in class in the 4th week, as marked on the syllabus. So we'll talk about it in class, no doubt, as we get close to the time. The material that's covered is just from the first 2 weeks. The first two properties, first two activities were fluid properties and pressures at a point. And indeed, the individual tests on the Monday includes dimensional analysis and the ideal gas law. On Wednesday, interfacial tension, surface tension, and on Friday, pressure at point and manometry. So we'll talk about those individual components here. This is just a review. Certainly you should review the other stuff that we've talked about in class and the notes you might have taken and the book as you desire. But I think I tried to give all the equations that you'd need on such a test within reason. I'm not trying to trick you. I don't think hopefully none have been left out in error. You can test previous exams to see whether the material that was on the exam was actually covered in the review if you feel nervous about this at all. Okay, so anyway, so just to quickly go through this, obviously the first 2 weeks were 3 hours of classes in each week, and so 6 hours of material we won't go through. I imagine this will take about 20 minutes, but I can summarize the kinds of things that you would need to know for the different Monday, Wednesday, Friday events. Dimensional analysis, we work in terms of both dimensions and units. The dimensions that we use are typically mass, length, and time, and temperature, if temperature exists. And the alternative way of doing it is in force, length, and time. Those are the dimensions. If we want to link the mass and the force, length, and time systems, we note that 1 Newton, I don't know why that hasn't come out, 1 Newton is equal to 1 kilogram meter per second squared by definition. It's the 1 Newton is the force needed to give 1 kilogram an acceleration of 1 meter per second squared. So the dimensions of mass, length, time, and temperature, theta in this particular case, they are raised typically to an exponent, A, B, C, or D in this particular case. And the units for SI, which we'll use exclusively, are in terms of kilograms, mass, seconds, and degrees Kelvin for the different quantities. If we want to be able to calculate something in terms of those quantities, what you need to do is take the parameters that you know and convert those into something that you want to know. So for instance, if you wanted to know what viscosity was, you could rewrite Newton's law of viscosity in terms of the individual components that you know. Y, which would be units of length, velocity, which is units of length over time, and a shear stress. A stress is equal to a force over an area. Area is length squared, and a force is equal to mass times acceleration. So this is kilograms, and this is meters per second squared. And so you can use that to be able to hone in on the parameter you need to get. You've done that already in your assignments. Ideal gas law, pressure is equal to density, gas constant, and temperature. Pressures and temperatures have to be in absolute pressures and absolute temperatures. This is a gas constant that changes with the gas that you're talking about, and this is the individual density. Density is defined in terms of mass divided by the volume over which it applies. I guess we talked also about isothermal compression, in which case temperatures are the same, so that the absolute pressure divided by the density are always constant if it's isothermal, and if it's isentropic, the same occurs, except there's a power to the power k, which is typically of the order of 1.4. In terms of dealing with these systems, if you have a balloon with a flexible membrane, the pressure acting on the outside of the balloon, because the membrane is so flexible, is the same as that interior, and so sometimes you need to be able to make that assumptions. I don't think we have a balloon question this time, but if you want to know why a balloon rises, it rises because the density decreases, and the density will decrease if either the pressure decreases, you use a different gas, or you increase the temperature of the gas in the system to make it rise. You can't really change the pressure in the system because you'll collapse the balloon, but you can certainly put helium in a balloon, less dense than air, and you can certainly heat up the gas to make it less dense than air that surrounds it. Surface tension, we talked about in terms of a capillary. Capillary rise in a tube is due to the attraction of the liquid meniscus onto the glass capillary tube. It rises to a height hc driven by the surface forces, which will be at some angle to the glass, and you can resolve that angle vertically to be able to balance the weight acting downwards with the surface tension acting upwards. If you're not given an interfacial tension angle, best to assume that cosine theta is equal to 1. In other words, it's parallel to the glass, easiest way to do it. If you resolve both the weight downwards, which is equal to the volume, hc times the cross-sectional area, times the density times acceleration, this is w on this left-hand side. And if you equate that to the circumferential force acting upwards, circumference is this, interfacial force per unit length is this, and cosine of the angle, maximum value would be equal to 1 when this angle is equal to 0. If you cancel the terms that repeat, you end up with a magnitude of the height rise, which is given by 4 times the interfacial tension, the diameter of the tube, and the unit weight of the fluid. Hc increases with increasing surface tension, and increases with reducing capillary diameter. So we know those. I think you did an example on your homeworks of a bubble. What's the surface tension that's in a bubble? It has the surface tension on the inside and the outside. If you wanted to look at the force that's acting upwards in this, it's equal to the area of the bubble divided by the pressure that's acting on this, just as a free body diagram. So you can always take an area multiplied by a pressure that's applied on that area and turn that into a force, as in this term here. We use manometry to measure pressures at a point. The essential idea is that you can look at 2 points in a fluid, and those 2 points, if they're simply connected, will have the same pressure acting, as in this horizontal line going through point 2 here and this point here. And if you rise up to get to another location, you change through the static pressure within that tube. And so you can always work your way through a system, in this particular case, from say point 1, where you might know the pressure. If this was atmospheric, then this would be 0 gauge pressure. You go down, so the pressure increases by a height multiplied by the unit weight of the fluid, and that equals the pressure here. And because this is simply connected to this point here through the fluid, then the pressure here and the pressure here have to be the same. We know that because when we look at the fluid static equations, the pressure changes as we go horizontally are 0, which means that on a horizontal plane that's simply connected, the pressures have to be physically the same. The manometer rules are that if you go down in a fluid, you increase the pressure. If you go up in a fluid from here, you reduce the pressure, negative. If you're in a gas, then typically a gas is very light compared to a liquid, maybe 1,000th of the density, and so you can typically neglect the pressure change in that. And if you're in an evacuated space, then the minimum pressure you can have is the vapor pressure of that component. If you look at fluid pressures at a point and extend them, we talked about the equations that describe the change in pressure with depth. The change in pressure with depth is equal to minus the unit weight. The behavior is different if you look at the behavior in a liquid, where the density is constant. If the density is constant as you go down, then this equation is correct as it is for gas. But this the unit weight is constant because the modulus isn't allowing compression. And so you can get the change in pressure with depth just by using this integration, if you like, of this expression. This expression. This is just integrating that expression, which says if you want to get the pressure at any particular point, you use the pressure at some other location and you go up and down some elevation h and multiply by the unit weight of that fluid if it's static. In a liquid, it changes linearly with depth, and that's what this expression represents. If it's a gas, you have to use the density, which is controlled by the ideal gas law. And you can use that to show that as you go up in the atmosphere, you start off with a high density here, high unit weight, because it has a large pressure on it, which is compressing it. And as you go higher and higher up into the atmosphere, it ultimately asymptotes to zero pressure absolute. The ideal gas law, as we noted before, you have to use absolute pressures and absolute temperatures. The absolute pressure in the atmosphere as you go into space is an absolute pressure of 0. The absolute pressure at sea level, due to the weight of the atmosphere on top of us, is 100 kilopascals, roughly, 101 something, but use 100 in the test if you need it. And as we go down a depth, the increase in pressure with the unit weight of fluid is much faster than in the gas. This curve is 1,000 times more rapid in terms of increasing in density in pressure than this curve, just because of the unit weights of gas, which is about 1 kilogram per cubic meter versus liquid water, which is 1,000 kilograms per cubic meter. So that's pretty much it. I think all the equations that you ultimately need are in this sheet. What I will do with this sheet is I will make a copy of it and attach it to your exam sheet on the days of the test, and so you can use this. But I would think about these individual expressions, not just knowing what they are, but also knowing how to use them. That's, I think, the key to this course, is being able to understand exactly how you use these different expressions in a creative way. Okay, thanks very much.